Okay, everyone, time to start. I wasn't sure if Patrick was going to come. I thought he wasn't, but little misunderstanding. So thanks for doing this. Before we start, you have all installed SDK, I'm assuming? Okay, working on it. Don't waste time. As I said, the first 10 points are really easy, so I would jump on them right away. Just a suggestion. And then I just got an email, all the faculty got an email about final examinations, and we don't have a final here. I just wanted to reiterate that the last exam we do the last day of class is not a final. It is testing you on what we do between the second and the last exam. Same for the other ones. Of course, if there is some knowledge that you should have from the beginning of class, I mean, what an angular velocity is or these kind of things, it's, you know, you have to know it, but it's not a cumulative exam where I test you on everything. It's not a final exam. Because there's some people, some colleagues here who give exams during the semester and they do actual finals during the semester, which we're not supposed to do. So I just want to reassure you guys that that's not the plan. And you can check it from last year. The exams are there. You can tell that it's not a final exam. Okay. I think that's all I wanted to tell you. Let's finish what we were doing, which is the following, and it will also allow me to introduce some theory that we actually need for Astro. So we said we have a reference frame, A, and its coordinate system, the origin is O. We have another generic reference frame called B, and its origin is called O prime, and then we're looking at a particle. So what I'm doing these days is refreshing dynamics for particles, because that's what we're going to use for the most of the semester. At some point, we'll probably need some rigid body mechanics, and I will refresh it then so that it's ready to go when we need it. And we said, okay, I'm going to call Rp the position of this particle with respect to the origin of A. I'm going to call Rp with respect to O prime the position seen by B. And then we close the triangle with this, which is the position of the origin O prime with respect to O. And we wanted to find relationships among velocities that these two observers see and accelerations. We did the velocities. I'll just redo it real quick. Position of P, if you close the triangle, is the position of O prime plus the position seen by B for the same point P. So we want time derivatives of these vectors in A. So we want, for example, the velocity of P with respect to A. That is going to be, we said, the velocity of O prime seen by A, plus we apply the transport theorem on this. Why? Because most likely that vector will be expressed in this basis fixed in B. And we obtain what we call the velocity of P seen by B plus omega B with respect to A crossed with Rp with respect to O prime. And we had to do the acceleration, right? So we just start from there. I'm going to start here because it's going to take a little more space. So time derivative of the velocity of P measured by A taken with respect to A, it's the acceleration of P in A, which is going to be equal to what is the rate of change of that with respect to A. It's the acceleration of O prime seen by A. What about this one? What do you want to do with this one? I think I'm going to do the transport theorem again because it is what B can see. So I'm going to apply this. Rate of change of this vector with respect to B plus omega B with respect to A crossed with the vector itself. And that's that. Plus time derivative with respect to A of that cross product. So you do the time derivative of this cross with the second plus omega cross with the time derivative of Rp with respect to O prime. Stop me if I'm going too fast. Probably not. This is stuff that you should have seen. Alpha B A. Remember, it doesn't matter if it's B or A taking the rate of change of this vector. For once, it doesn't matter. Crossed with Rp with respect to O prime plus, I'm going to put it down here, plus omega B A crossed with, I would have to compute the rate of change of this vector here with respect to A, which is what we did last time here, right? And it came out to be this piece, right? So I'm just going to put that in here. Velocity of P with respect to B plus omega B A cross with Rp with respect to O prime. Rp O prime, I think It's almost done. We have acceleration of O prime seen by A plus, what do you call this time derivative here? That's the acceleration of P seen by B, right? This is what you see if you're attached to that reference frame. Plus, I see this cross product twice. So 2 omega B with respect to A cross with velocity of P seen by B. Who is teaching the class before me? There's pieces of chalk all over the place. I had a professor in college who used to do this teaching chemistry. Can you imagine that? With all the little letters and numbers. He wouldn't erase everything. That was great. Okay, what else? The alpha piece. Alpha B A cross with R P with respect to O prime. And then the last one remains what it is. And I think I'm going to put it down here. B A cross with omega B A cross with R P O prime. And so this is the other, and remember that this is equivalent to the acceleration of P seen by A. Only I've used the transport theorem because probably there are some of these vectors, this one and then this one, that will be expressed in B. Right? So this is one of the second of those formulas that you may have been asked to memorize at some point in life. And you really don't have to because you can derive them. And every time you solve a problem, it's different. So this is the general formula if you want to. But this is what you will call the Corioli acceleration. This one probably doesn't even have a name. This is the centripetal one. But again, there's no point in memorizing them. And one more comment. When you apply the second law of Newton, F equal ma, and say that this observer is inertial, then what do? Well, you have expressed the acceleration this way, so you start having m acceleration of O prime in A plus m acceleration of P in B, yes, plus, guess this piece what it is. This is your Corioli force, right? In respect to B, and so on and so forth. So this is what people call Corioli force, for example. It is not a real force. In fact, they're called apparent forces. It's not coming from attraction of anything. It's not coming from physical interaction. It's not coming from anything because it does not exist. It's just an artifact of you using the transport theorem because it's convenient. Okay. So I wanted to refresh this because we will use it, possibly next time. And also, it gives me an excuse to show you one problem, which is a problem for a graduate dynamics class, but it is really theory that we need in a class like this, where we can show how good of an inertial reference frame this planet can be if we choose axes in a certain way. So everything is on my website, as you know. So this problem, the exam for the astrodynamics, the analytical dynamics class is there. This projector hates me. Yep. Okay, it's on. So if you go under the teaching page, under EML 5215, here it is. So this is this is the design class from last semester. This is Astro from last year. Everything is there. And the same for this one, analytical dynamics. So if you go to exam 1, there is a question I asked them, which is really theory we need. I think it's the third one, right here. Okay, so we said, consider the following simplified two-dimensional model of a Sun-Earth spacecraft system. The Sun is located at point S. There is a little drawing there, but I'm going to redo it here because I don't want to reduce the text size. Okay. So Sun is somewhere down here. And the Earth is somewhere around the Sun, going around the Sun on its almost circular orbit. And spacecraft is orbiting the Earth, and we called it P. So this is going to be a 2D case of what I've just done in 3D. More or less. Just much simpler. Suppose that we have a coordinate system that has an origin in the sun and a basis EX, EY, Z. We have big EX this way, EZ is coming out. We're not really going to use it much. There's the sun here, and EY. And suppose that this basis here is fixed to an inertial observer. So you can call these, let's just call it S again, but this is inertial, right? This observer is inertial. Absolutely stationary. And that the Earth does not rotate relative to the sun. Also, the distance Sun-Earth is a constant r. So this vector that goes from the sun to the planet has a constant magnitude r. The angle between EX and Sun-Earth line is this angle here, theta, which is omega t, and I believe at some point I'll tell you that omega is also constant. Yep. Finally, position vector of spacecraft relative to the Earth is called little r. This here. Okay. And so, using this information, determine an expression for the acceleration of the spacecraft relative to the sun in terms of the variable little x, little y that I have to define, constant r and omega, time, where x and y are the components of the position of the spacecraft relative to the Earth. I know it's a mouthful. In the basis EX, EY, Z. So basically what I'm saying is I take this basis, I just imagine that I use it here. Okay? It's the same basis. Easy, sticks out. And so the projection of this little vector on this basis relative to the Earth is little x and little y. And then we'll read the rest. The point of the rest is demonstrating, as we'll see, that for certain values and certain orbits, certain distances of the satellite from the Earth, this basis here, this reference frame centered at the Earth can be approximated to be inertial. You agree with me that this is not inertial, right? This one, assume it's absolutely stationary, whatever that means. If the planet is going around, even if the orientation of this basis doesn't change, you're still moving on a circle, which means you're not translating. You have a non-zero acceleration of the points of that frame. So this one here that I'm going to call, I'm going to call it E, the Earth's frame, it's not inertial by definition, but it can be used as an inertial one, given the numbers that we use later. But let's do symbolic calculations first, which is I want to find the acceleration of P with respect to the sun, right? That's all I want. This is a very simple two-dimensional problem. But what would you do? I mean, the solution is online. I don't know if you have looked at it, but I do the same thing that I've done before. There's a triangle here. The position of that satellite with respect to the sun is this vector here that I don't want to draw because it's going to be a mess. But let's call it r with respect to the sun if you want. Man, I don't like that. Just rp. How about that? So rp is the addition of big R plus that little r. And I've been told the following, that big R is nothing else than r cosine of omega t big EX plus r sine of omega t big EY. That takes care of this vector, sun to the Earth, plus little x EY plus little y EY. I use the same coordinate system for two frames, except the origin is different. So, same basis, not the same coordinate system. Then you take its time derivative, velocity of P with respect to the sun is, well, that's what it is. Minus r big omega dot sine omega t big EX plus, let's see, r omega dot cosine omega t EY plus x dot EX plus y dot EY. No surprises. And the next one is also going to be no surprises, which is the acceleration. Acceleration of the satellite with respect to the sun is another time derivative of that, minus r omega dot squared cosine omega t EX Let me go down here. Is there a minus now? Yes, minus r omega dot squared sine omega t ey plus x double dot ex plus y double dot ey. No big deal. Everything is expressed in the same basis. I don't have to do transport here. I don't have to do anything. And that basis is fixed with s. Yes?
Did you say that omega was constant?
Omega. Did I say omega is constant?
Yes. Yeah.
Yep, right there.
Okay. In fact, this is not omega dot. Right? It's just omega. Right? Sorry. Thank you.
Should be done.
Yep.
You did.
Is that? Did you have the same question?
You got rid of the dot.
Yeah, sorry. Yeah. In my mind, I was looking at this as an angle, so that was an angle dot, but that's incorrect. It's an omega t. The angle is omega t, so you take the rate of change of that, and since omega is constant, that's what you get. Thank you. Looks better? Okay. Yes. So what was the next question? Well, that's the first question. That's it. One thing to keep in mind is, notice that this piece here is, what is this? Forget about this additional term here. What is that one? These are all accelerations, right? This must be an acceleration. Acceleration of the Earth with respect to the Sun, right? Yep. Okay. So we go to the next question, which is the important one. Now, suppose that these numerical values are actually given. So that's the actual distance Sun to our planet. That's the angular velocity on its orbit. Takes a long time to go around, an entire year. In astronomical calculations, and this is what we're going to do in this class. So this is a problem that it's basically theory that we will use. What it is often assumed is that the Earth is often considered an inertial reference frame, and that coordinate system attached basically to E, it's called ECI. We'll call it ECI. You'll hear this a lot, meaning Earth-centered inertial coordinate system. So using those values, justify when it is reasonable to consider the Earth to be an inertial reference frame. And by the way, there is a huge hint here that you're supposed to use to solve the problem. And you wouldn't believe how many graduate students completely ignored this piece here and just went ballistic trying to justify this without even looking at this hint, which is impossible to do. But they just ignored it. So, but before we look at the hint, and then there's another question, if I change numerical values, does the assumption still hold? But that's basically the same question. So what do you want to demonstrate here? I want to demonstrate that this is also inertial. So in other words, what is the equality that I would like to prove?
X dot and y dot dot are very small.
I'm sorry? That they are what?
Show that the remainder of the box is very small.
This is small, right? Right. So, because if you look at this expression, that's why I underline what this is. This is basically, it's the acceleration of the Earth with respect to the Sun, which is this entire piece, plus, what is this? This is the acceleration of P with respect to the Earth, right? So if this is my inertial acceleration for the satellite, measured by an inertial observer, I want to use this. So this has to go away somehow. Has to be much smaller. Does it make sense? Make sense? So this has to be something I can ignore. And so that's when you start using that hint. Okay. Can I erase this? I don't think we're going to need it. So let's see what the hint is telling me. Yeah, I don't need this either. All right, in your justification, use the following information. 1, the acceleration of an orbiting object due to the Earth's attraction, which is the force we're going to use next time, and we start talking about gravitational forces, and we really start doing astrodynamics. next time, it's given, seen by an observer in the ECI, is this. So in other words, that AP with respect to E, what an observer attached to the Earth sees is that. It's R double dot, of course, and it's given by this force model. Minus mu, this is a given constant, norm of the vector R itself cubed times R itself. This constant, the gravitational constant mu, is given here, so it's just another number. Okay, that's the first piece of information. I'm telling you what that looks like. And then, so this, if you want, it's also equal to x double dot EX plus y double dot EY. Okay? And then the other suggestion is compute the magnitude of this acceleration at multiples of the radius of a geosynchronous orbit, which is 42,000 plus kilometers. That's the altitude where your satellite is going around the planet. I don't want to talk about orbits yet, but if this is your planet, you choose an altitude, a distance from it, where the time it takes to go around one time is equivalent to a day, 24 hours, give or take. Yes?
So what was that ECI?
Earth-centered inertial.
Oh, okay.
Yep.
Also, why is it A why is it number? Why is AE on both sides of the equation? Should it be
No, this. Sorry, that was a leftover.
equal to XP?
Yeah. Yep. So, in other words, I want to see when this assumption of being able to ignore this piece is going to break down. So, in other words, I want this piece here, the magnitude of this acceleration, to be much smaller than this. And I don't have a calculator here, but I do have the solutions, and I can show you what these numbers look like. So, the magnitude of this, first of all, of this vector here, what is the magnitude of this? How do you? That's the vector itself, right? What would be the magnitude of this? It's mu over r squared, right? Make sense? I have an r cubed here, I have another r here. If I take the norm of this vector, this is what it is. And then I have the acceleration of the Earth with respect to the Sun, which is the one that I hope it's going to be small enough compared to this. It's the norm of this vector that is highlighted here. What is the norm of that? What do you think? R omega squared. Do we all agree on this? Sine, cosine, right? Cosine squared plus sine squared gives you 1. So basically what they had to do is show that this is much smaller than this, and they had to do it. My suggestion was, with those numbers I gave you, start with r, little r being this value, 42,164 kilometers, compare, go twice that altitude, compare, go 3 times that altitude. That was the line of thinking. And if you look at the solutions, I have the numerical values here. That r omega squared, this is just to show you how exams will look like. Will be questions I prepare and solutions I give you, most likely handwritten unless it's a MATLAB code. Meaning, don't waste time trying to find the solutions anywhere because I make them up. So just think about solving the problem. MATLAB, if it's code, I'll give you the code, yeah. Does it make sense? No, MATLAB in the exams, no. No. In 15 minutes, forget about MATLAB, no. No, I'm not that mean. Let's see, question 3, where is the value? Here it is. Okay, with those numbers I gave you, you get 0.0059 meters second squared for the actual, real distance from the Sun and real angular velocity of the Earth around the Sun. So keep in mind that the norm of this at the surface of the planet is about 9.8, of course, meters second squared. The acceleration of gravity that we have here. If you go to 1 time the geosynchronous altitude. There's no comparison. This is 2 orders of magnitude smaller. I don't have a value, but you can play with these and substitute the numbers. You have to go 6, 7 times higher than a geosynchronous orbits to start seeing that these numbers are comparable. So you're fine if your satellite is flying lower than 6 or 7 times the geosynchronous orbit. And if you think about that, 5 times that value, you're basically at the moon almost. So most of the satellites that we put into orbit around this planet don't go that high. Geostationary, geosynchronous orbits are really pretty high. There's some cases where we go higher than that, but it's pretty rare. So the answer is yes. This is a reasonable approximation. This term here, this piece here, you can kind of ignore it, and you can say that the acceleration seen by the sun for the satellite is the same that you would see from the Earth. And that's exactly what we'll do for most of our astrodynamics class. Then if you go to the other values I gave here, where all of a sudden the sun and the planet are very close, and the Earth goes like crazy, 1 radians per second around the sun. Of course, that doesn't hold anymore. If you just do your calculations, that r omega squared becomes very big, and it doesn't work anymore. So I wanted to show you this problem just because it is something that we're going to use. We're going to use ECI. And for now, I haven't defined it formally because it's not the time to do it. I want to do something else today. But at some point, we'll do it in 3D, where we'll say, OK, this basis is going to, the ECI basis is going to be centered at the planet. It doesn't rotate with the planet. And the directions, call them X, Y, Z, that we choose are pointing in certain directions in space. They actually change every 25 years, if I'm not mistaken. They get updated depending on positions of constellations. So we'll go through that definition. But that's what we do. We look at satellites' motion. We will look at satellites' motion in this basis because it's good enough for what we're going to do. Make sense? Questions? Concerns? Have you seen this problem before? Go ahead.
Why don't we just effectively ignore the x double dot, y double dot?
No, we're not ignoring that one. No, that's the one I keep. Make sense? This is what I want to ignore. This is due to the acceleration of the Earth around the sun. So let me, I think it's better if I just rewrite it here. I would like to see this. Acceleration of P, remember, is the satellite. With respect to the sun, is the inertial acceleration of the satellite. And then this is the acceleration of the Earth seen by the sun. And then I have the acceleration of the satellite seen by the Earth, right? I would like this to go away so that I can sit myself here rather than the sun, because I'm not able to sit in the sun and look at the satellite. But if I can say that the acceleration I measure for the satellite, it's more or less inertial, what the sun would see, then I'm fine. I can use Newton's second law and all the principles that I know require an inertial acceleration. Make sense? And that's exactly what we do. I mean, there are effects due to the fact that the Earth is not inertial, but they are very, very long-term effects, and your orbit has to be very, very high. So it becomes something that you don't usually take into account. Any other questions on this? Promise next time we'll talk about gravitational forces. But there is one more thing that we use in Astro, and that's angular momentum, and it's about time to refresh that one. And that is really the last piece of dynamics I want to touch on for particles. Do we remember the definition of angular momentum of a particle? A particle of mass m, of course. Particle of mass m with respect to a point q, generic point q, and also measured by I'm just going to say n, an inertial observer. Do you remember what the definition is? This is not a law, this is a derived result that helps a lot when you're solving certain types of problems, and we'll start an example that you probably will finish. So H, computed with respect to a generic point Q, seen by an observer that is inertial, or any observer really, but we care about the inertial here. It's defined as position of the particle minus position of that point Q you've chosen, crossed with mass of the particle, velocity of the particle with respect to the same observer, minus velocity of that point I've chosen with respect to the same observer. That's how it's defined. Of course, if this point Q is fixed, this goes away, it simplifies, but in general, it's not fixed. And then we have a derived result when you do a few calculations and use second law of Newton to prove this, that the rate of change of this vector here, still with respect to n, is given by the moment of all forces with respect to Q that are applied to that particle, minus position of P minus position of Q crossed with ma of Q. Okay. And finally, well, definition of moment of the forces, it's this Rp minus Rq is everywhere. Rp minus Rq crossed with F. That's it. You remember that? Angular momentum is used and abused in astrodynamics, so refresh it. Let's see what I have. I have this fancy moving pendulum problem that I really like. And we'll start and then you finish, because I think it's going to take a while. Or maybe not. Okay, so I have a circular guide which is attached to an inertial observer. I call it G. Actually, let's call it N because I called it N there. Its center is here, and then call it O. And then the hinge of a pendulum is attached. It moves on this guide. So here I have a pendulum length L. The mass of this is negligible. I have a particle of mass M. We have this angle with the vertical, which is called theta. And we have this motion here, alpha of t, that is given, or not. Let's say that it's given for this problem. And maybe there is gravity. Okay. So what else? I think that's it. You want the equations of motion, as usual. And of course I'm going to do it that way. Yes?
What is theta between?
Oh, vertical direction and the direction of the pendulum. Can you see it? Okay, so before we even start with this, well, first of all, I'm going to start solving it with angular momentum just to show the advantage of doing it. Then you guys go home and try to solve it with standard Newton's second law, just to see if it's more or less painful. So, what is the first question we ask ourselves? How many equations I need, right? So this is a prescribed motion, right? I'm telling you that let's call this point Q. So how many equations do you expect? It's a planar problem. 2 equations, you sure? Cannot be 3, right? Everything is in 2D here. So if it's not 2, there's no more choices. It's 1. Do you see it's 1? So if the position of Q is given at any time, basically I have a function of time alpha that is telling me how this radius here R is moving around. I'm really left with theta. That's the only, I only have 1 degree of freedom. The position of Q, if you give me a certain time, I know where it is. And then finally, to tell you where P is, I have to find a differential equation in theta, and I'm done. and solve that differential equation. So I need one equation, right? A simple pendulum, you would probably tell me right away it's one equation, right? Do this, theta, this length is fixed. You would tell me right away, yeah, I need one equation here, right? 1 degree of freedom. You are in plane, the particle will have 2 degrees of freedom, x and y, for example, but I'm constraining it to moving around this point. The only difference is that this point is not moving with respect to the inertial base frame. Here it's moving, but it's a prescribed motion, so it doesn't make any difference. It's not a degree of freedom. That point, Q, is not free to do whatever it wants. I tell it what to do. So that's the start. Always ask yourself, again, where you're going when you're solving a problem. It's one equation in theta. So please do try to solve it at home. I'll start with that, and you see that it will just come up as a single equation. I don't find more equations that are not needed. I will get to the point right away. If you solve it with Newton's second law, you will actually be solving 2 equations, and then you have to eliminate an unknown force, as you will see. Yes?
If it was like a pendulum not fixed on a circle from O to Q, and then another pendulum from Q to P, would there be 2 equations of motion at that point?
Yeah, you will. So that alpha will become another, for example, degree of freedom. Yeah, yeah, absolutely. Yep. In that case, yeah, you will have to find two equations. Just alpha is not a function of time that is given. Yep. That's another nice problem to solve if you want to try. Okay. So let's try to do it this way. It's very simple. Well, some vector calculations, but it will get rid of one thing. I'm going to jump ahead of myself. I mean, you guys have taken dynamics already. At some point, when you find equations of motion and you switch to the kinetics part, you have to figure out the forces, right? And what you do is the free body diagram. So you just look at that particle and say, hey, I have gravity that is acting on it, and then what else do you have? You have what we call a reaction that is going to be along this line, PQ, right? Well, since I'm going to choose Q to do my calculations with the angular momentum, what is going to happen is that in this expression in particular, Q, that unknown reaction is going to vanish. The cross product of Rp minus Rq crossed with big R is going to be 0. That is the beauty of angular momentum approach, is that you can usually get rid of unknown forces. So that's why one equation will pop up immediately, and just one, while if you do it the other way, in Newton's second law, you have 2 equations, R will be there, you have to eliminate it. You can make it disappear, but it will take an additional step. While if you do it this way, it doesn't. It doesn't appear. So, okay, let's figure out those vectors. That's all we have to do. Okay, let's start from H. Well, what is Rp minus Rq? Actually, I'm going to go one piece at a time. What is Rp minus Rq? Oh, I haven't defined basis, right? I'm really going a little too fast. Okay, the origin of the basis attached to the inertial, to the ground, is going to be O. And I'm going to choose Ex this way. I'm going to choose Ez pointing at you, and Ey pointing up, for example. While the other reference frame I'm going to choose is the pendulum itself, origin at Q, and let's say little ex going from Q to P. I'm going to recycle Ez pointing at us, and then Ey is going to be whatever it comes out to be. So I have my 2 bases here. Okay, with those, we'll go back there. What is Rp minus Rq? Lex. Yep, it's a vector. Yes, done. Let's figure out the velocities. Let's talk about Vp, for example. So Rp is OQ, vector goes from O to Q plus this Lex, right? Which is also equal to R cos alpha Ex plus R sine alpha Ey plus Lex. So its velocity with respect to n, which is what I need to find, that's where my omega dot was coming from. I was jumping ahead to this problem. Here there is an alpha dot r, alpha dot, the minus sine of alpha ex plus r, alpha dot cosine of alpha ey. What is the rate of change of this vector with respect to n? Nope. Nope. It's not 0. Think about what's happening here. This vector Lex is a vector that points from here to here, right? This thing is moving. It's going to change with respect to the inertial observer. So what would you do there? Transport theorem, it's always the same story. Okay, rate of change of this same vector with respect to, I didn't give it a name. What do you want to call this? A? I'm not using A, right? Nope. A plus omega of A with respect to n crossed with the vector itself. As always, stop me if I go too fast or jump something that I assume it's obvious, but it's not, please. Make sense? So now this is 0. This, I agree, it's 0. If I am moving with the pendulum, I don't see that vector changing. So this is 0. And then I am left with the angular velocity of A with respect to n. What is the angular velocity of A with respect to n? It's only theta dot. The way I've defined it is it's pretty simple. So theta dot Ez crossing L Ex, which is giving me L theta dot Ey. Okay? We can put it there. Can I put it there? I think so. Okay? And in solving these, I've also found velocity of q with respect to n because it's this piece right here, right? Agree? It's these first two vectors here are the rate of change with respect to n of OQ, which is the velocity of q. So that second piece, Vp minus Vq in n, it is this vector, this entire vector, minus Vq, it's only L theta dot Ey. And so my HQ in n is L Ex crossing L theta dot. There's a mass missing, right? Yes. M L theta dot Ey, which is what? M L squared theta dot Ez. That's usually what happens when you use angular momentum, especially for 2D problems, is that everything gets projected on the normal direction. That's the definition of angular momentum. You're crossing vectors in plane, you get stuff out of plane. Make sense? Another question? Nope. Okay, so if we've taken care of the first one, let's do the other pieces. Which one do you want to do? How about the rate of change of these? It's very simple. Since, well, yeah, I'm sorry, separate stuff. It's the rate of change of this vector in n. No brainer. Theta double dot Ez. Why can I do this? Big Z, big Z are the same thing. They're fixed in n. Yeah. Okay. What do we want to do now? Let's start up here. I don't want to erase the sketch. How about this one? MQ. Then we'll go back to this one. Okay, it's RP minus RQ, right? And we've done that. It's LEX, which is crossing the forces that I have. And the forces are R, which is pointing along EX. I don't know, plus or minus, it doesn't matter. Unless I have to solve for it. Plus, actually let me just write what it is, minus mg big EY. Okay, since this one can be expressed as REX, you see that it goes away. That's usually what you do when you decide to solve a problem with angular momentum. You pick a point where hopefully you're going to kill as many unknown forces as possible. Okay? And so I am left with this thing here, minus MLG, and the cross product of EX and EY. Crossing two vectors belonging to different bases. It's not illegal. I can do it. What is that? Can you see it? Do we want to sketch a few things here maybe? This is the situation. You have the big E's, and then you have the little EX that is pointing this way, and this vector is theta, right? So I'm crossing this guy with this guy, and it's definitely going to point towards us. And we know the definition of cross product, right? The magnitude, these are two unit vectors. So the magnitude is going to be the sine of the angle between these two, which is pi minus theta. But the sine of pi minus theta is the sine of theta. So at the end of the day, this is minus MLG sine of theta, little easy. No unknown forces are left. R is gone. I will not see it again. Okay, so we have computed this. We have found that this is, we're missing AQ. Yeah, we have to do it. All right. Which part do you want me to erase? I think I can erase here. Oops. No, wasn't supposed to do this one. So I have to take the real change of these, right? It was a minus? Thank you. Yep, that was a minus. Okay. Acceleration of Q with respect to n is the rate of change of this part here. I have a minus r alpha dot squared cosine of alpha EX, and I'm going to have to stop in a couple of minutes, minus r alpha dot sine of alpha EY. That's it. So at the end of the day, you will have, your equation of motion is coming from this one, of course, right? That's where it's coming from. The second time derivative of theta is here. So you will have an equation that will look like this. ML squared theta double dot EZ is equal to M of Q minus MLG sine of theta EZ. See, everything is on EZ. And think about your vectors. The moment of the forces that are involved here has a minus component on the z-axis. It makes sense to me. This gravitational force is pushing down. It's going into the board. The moment of that force is going into the board as opposed to EZ, right? And then that additional piece, there is this minus RP minus RQ, which is LEX. We figured that out. And you have to cross this with M, all that, which you guys can probably finish at home, but it's the same story we've seen before. Yeah, you're crossing vectors from different bases. It's really not a big deal. You just have to figure out the angles that are involved here. But everything will be, of course, pointing in the z direction. So you have one single equation, all projected in the z direction, that gives you a second order, which is what you want, differential equation in the only variable you need because it's 1 degree of freedom. Finish this, resolve it, Newton's second law, and see the difference. And as far as I'm concerned, dynamics refreshing is done. We'll start astrodynamics on Wednesday.